Today we're going to be talking about inelastic collisions. So what we talked about last time with the elastic collisions was essentially if we have two balls and then let's say that they're sent at each other, they'll get to a point to where they collide, but then they're going to be bounced off and they're going to go in opposite directions. Or if we go with the practice problem I did last time, one ball is going faster than another one, overtakes it, and then we had a change of momentum. We had velocity changes for these objects. So today we're going to be talking about inelastic collisions. So the big difference between the two is with an elastic collision, the two objects bounce off of each other. With an inelastic collision, the two objects are going to be attached to one another. They're going to stay the same. They're going to be like wrapped around each other. They're just going to be together. They're going to be stuck together in some way. So right now what we have up in the upper left-hand corner there is the law of conservation of momentum. We're going to alter it just a little bit just because with an inelastic equation, starting off with the two objects are going different velocities. But afterwards, since the two objects are stuck together, the two velocities are the same. Since they're stuck together, object 1 and object 2 will be going the same velocity. So we're going to rewrite this just a little bit. So we're going to start off the same way. So mass of object 1 times the initial velocity of object 1 plus the mass of object 2 times the initial velocity of object 2. But now, these two final velocities are going to be the same. So I'm just going to pull VF by itself out. And then just algebra, since these two things are the same. If we factor that out, we're going to be left with the mass of object 1 plus the mass of object 2. All right. This is one of those times where I'm really excited that factoring in algebra, has a real world purpose. Sorry, math teachers. People that love algebra. I love algebra. But there's some of that stuff where I'm like, I don't understand how this is going to be useful. And this is where we see it. So, okay, side note over. I'm done nerding out. So the two different objects moving different velocities, after they collide together, they have the same velocity, and it's like their masses are just added to each other. It does affect the math just a little bit, but it's not too bad. So let's jump into question 4 there. So a 0.11 kilogram hockey puck. All right, let's just call that hockey puck the first object. Okay, so we have the mass of object 1 is 0.111 kilograms. It's moving at 55 meters per second to the right. All right, so I would say positive in this case is to the right. Negative will be to the left. Okay, so let's just say that the initial velocity of object 1 that they give us there, the 55 meters per second to the right, we're just going to say that's in the positive direction. Is caught by an 80 kilogram goalie at rest. All right, so the goalie is going to be object 2, and they have a mass of 80 kilograms, and they're at rest. Sorry. They're at rest, so the initial velocity of object 2 is 0 meters per second. All right. So the big question is with what speed or what velocity does the goalie slide on the frictionless ice? Or another way to think of it is, since the goalie's catching the puck, what's the final velocity for both of them? Since they'll be going the same speed since the goalie is catching the puck. So let's throw some numbers into our equation up here. So mass 1 is 0.111 kilograms times by the initial velocity of object 1, so 55 meters per second. We need to add the initial momentum of object 2, so we've got 80 kilograms. Oh, this one's easy. The goalie's initial velocity was 0 meters per second. So that'll make that math super easy. We're looking for VF here, so let's just leave it VF. And we got the mass of object 1, which is 0.111 kilograms, plus the mass of the goalie, which we said was 80 kilograms. All right, so we got some easy math here. Let's start off by 80 times 0 is going to be 0. So we've got, so let's take care of this 0.11 times 55. All right, so we've got 0.111 times 55. So the initial momentum of object 1 is 6.105. All right, let's just leave that 6.1. So we've got 6.1 kilogram meters per second. 80 times 0 is 0, so I'm not even going to care about that. This math is going to be really easy. VF's going to stay VF. 80 plus 0.111 is 80.111 kilograms. All right, so now algebra, if I've got VF times 80.111, to get 80.111 by itself, or to get VF by itself, I just divide both sides by 80.111. And when I do that, let me change my mouse sensitivity there for you all to see. All right, 6.1 divided by 80.111. So the final velocity is 0.076, what we're going to say. 0.076 meters per second. All right, so that puck is flying at the goalie. The goalie catches it, and he does have some velocity there, and so that he'll be moved backwards. So let's see how well I can do this. That's my puck. It's moving 55 meters per second. Let's give him some ice skates there. Okay, so that 55-meter puck, he catches it. The goalie will then be moving backwards at 0.076 meters per second. So assuming that goalie can apply any kind of forward velocity, any kind of forward force after he catches it, he'll make sure that, or they'll make sure that the goalie and the puck don't end up, in the net. I'm assuming they're playing hockey in this one, because it's a hockey puck. That would make sense if I had read my own question. All right. So really the key thing here, inelastic equations, is once you've identified it's an inelastic equation because the two objects are getting stuck together after the collision, just make sure that you're using this modified equation here. You can use this equation here if you know that these two velocities are the same, but I think for the most part this one's going to be easier for most people, just to kind of keep the number straight, and you don't really have to think about it too much. Yep, that's right. A teacher's saying don't think about stuff too much. All right, in any case, good luck with the problems.